Today it's my pleasure to welcome John Froehlich. So I actually got to know John many years ago when he was a master's student. He was a power user of early visualization software I was writing, which was great for me for a number of reasons, not least of which I then had a front row seat to watch sort of his ascendant career into one of the most dynamic HCI researchers today. He's probably familiar to many of you, having been an alumnus of this program here, where his PhD thesis work on sensing and visualization for ecological sustainability won the dissertation awards both here in CSE and in the university more broadly. And he's since gone on to a very successful early career at the University of Maryland, where he's won a Sloan Fellowship, a Career Award, I think something like 9 best papers or nominations, working in a large swath of interesting research topics in HCI. And today he'll be sharing with us his work on making for social change. Thanks
John. So much. So it's really awesome to be here back at my alma mater, and I'm very honored with the invitation. So the goal of this talk is to give you an overview of the work that I've been doing as a professor at the University of Maryland. And when I started in 2012, I founded the Makeability Lab, which is a research lablet within this larger human-computer interaction lab, which is a lot like what you have with Dub. And here's a picture of my group in 2013. And we've now grown to a rather diverse bunch of PhD, master's, undergrad, and high school students. And our mission is to design, build, and study interactive tools for societal change. We have 4 focus areas: environmental sustainability, health and wellness, accessibility, and STEM education. And throughout this work, we have a common approach, which is to sense or reappropriate methods to sense physical and behavioral phenomena, then to analyze this data using computational techniques borrowed from machine learning and computer vision, and then to build novel interactive hardware and software tools that are uniquely enabled by these approaches. And the research process itself is iterative, often starting with formative design, formative studies, including participatory design methods, which lead to informing prototype design, which we oftentimes evaluate in the lab, then do technology refinement with the goal of actually doing studies in the field. So this talk is going to largely focus on these latter 2 areas, accessibility and STEM education. But to give you a broader view of what I do, I just thought I would touch on the other 2 areas. First, with environmental sustainability. So as Jeff mentioned, this was the focus of my dissertation work, and I've continued to extend that as a focus area at the University of Maryland. So for example, my student Matt Moriolo and I are working in smartphone-based thermal cameras and building mixed initiative capture and analysis tools to allow non-professionals like citizen scientists to energy audit buildings at scale. As another example, I've worked in health and wellness. My collaborators and I have worked on ways of bringing in behavioral science to technology design for health promotion tools. And I've operationalized this in my own technology design, for example, in social fabric fitness, which uses social facilitation theory in these e-textile jerseys to support group running goals. And of course, these areas are not orthogonal. Oftentimes, there's really interesting intersections. For example, today I'll be talking about BodyViz, whose aim is to bring children into the scientific process through wearables, but also makes connections to the physical world through eating and exercise. OK, so now we'll be turning towards the 2 major research threads of this talk in accessibility and STEM education. So starting with accessibility, really the overarching goal here is how to make the physical world more accessible for people with disabilities. And I'm going to be covering 3 projects with a focus on the first one. So with Project Sidewalk, the key question is, how can we develop scalable solutions that map the accessibility of urban infrastructure? And then how can we use that data in unique ways to build novel interactive tools? So beginning with some motivation, 30.6 million US adults have a mobility impairment. About half of these have to use some kind of mobility aid, like a cane, a walker, or a wheelchair. And with our aging US population, this is only expected to rise. So despite this growing need, cities remain inaccessible. For example, there's a lack of curb ramps, there's physical obstacles, there's incomplete sidewalks, and in the worst case, perhaps a scene familiar to you, there's all 3 things at the same time. So the literature supports that accessible infrastructure has a significant impact on the independence and mobility of citizens, as captured by this interview about some of our work.
When I go to school in the mornings, I don't take the sidewalks. I actually take the street, and they shout at me from their cars. They're like, "Get off the road!" And it's like, I can't actually use the sidewalk.
And the problem is not just that accessible infrastructure fundamentally affects where and how people travel in cities, but there's currently no mechanism to figure out where cities are accessible and not a priori. In fact, the National Council on Disability notes that there is no comprehensive information on the degree to which sidewalks are accessible in cities. So we're investigating a twofold solution. First, to develop methods that mine massive repositories of online map imagery to figure out accessible areas of the world semi-automatically. And then second, and crucially, to try to uniquely utilize this data to build novel interactive tools for people with accessibility, for accessibility purposes. So in the background here, I'm playing a video of a beta version of our tool called Access Score, which gives you an at-a-glance interactive visualization of the accessibility of your cities using the data that we're collecting. So we have these sort of two-pronged interests here, and today's talk is going to focus more on this data collection side. So there's three kind of underlying questions. So first, is online map imagery even a good source for accessibility data about the physical world? And second, can we create interactive tools that allow people to find these quickly and accurately? And then finally, how can we use computational methods to try to scale our approach? So let's talk about this first question. But before I do, I just want to recognize this large team of students, as well as my computer vision collaborator, Professor David Jacobs. And this is work done with the lead students, Kotaro Hara, who's now a postdoc at CMU, Manaswi Saha, and Jin Sun. So this first question, is online map imagery a good source for accessibility data? Put another way, how well does Google Street View correspond to the physical world? Okay? And so to address this question, as I'm sure many of you have done as computer scientists, I deployed my students and I to physically audit the physical world. In fact, we audited 179 bus stops and 273 intersections, covering a total of 78 linear kilometers. And what we found is high concordance between the physical world and Google Street View. And this is actually in line with prior work in public health and urban studies. And though they've not focused on accessibility, our work adds to this literature. So it just turns out that city infrastructure doesn't change that rapidly, and not at least within the time frame of a GSV car driving back through the cities and refreshing their data. So the key here is that Google Street View is a reasonable proxy for studying the state of street-level accessibility. Let's turn to the second question. And to begin addressing this, we built an initial crowdsourcing system that has both a labeling interface and a verification interface. Labeling is a four-step process, so imagine that you're a user. Hopefully you'll see some problem in this image. So the first part is that you have to find the problem, and then you can label it using our pixel outlining tool. And then once you've done that, we pop up a little menu, and you have to categorize it. So either surface problem, object in path, missing curb ramps. And in this case, it's object in path. And then we have you assess the severity on a scale of 1 to 5, where 5 is most severe, which means that it's inaccessible for somebody who's in a wheelchair. And then you submit your data to our servers, and you're given another label or another image to label. In this case, an image without curb ramps. Verification is somewhat similar. Verifiers can accept or reject labels, as well as severity levels. So we had a 4-stage study method, starting with creating this data set. And for this, we downloaded 229 Google Street View images across 4 different cities. And this is because city infrastructure and accessibility infrastructure varies based on region. And then we attempted to collect this balanced data set. So for example, we had 50 images with sidewalk ending, 66 with object and path, and so on. Crucially, we also had 50 images that had no problems, which were used in part to evaluate false positive labeling activity. And the second part was generating ground truth. And for this, we had 3 independent researchers label all of the images in our data set. And then to aggregate it into one ground truth data set, we used majority vote. Okay, so for the third part, deploying our tools to the crowd, in this initial work, we used Mechanical Turk. And in total, we had 185 labelers, over 270 verifiers who contributed over 7,500 labels, 19,000 verifications. And the key thing here is that labeling is more than 3 times slower than verifying. Verifying is very fast, but labeling requires a higher cognitive load of actually finding problems and labeling them. And then finally, we compared our performance to that ground truth data set that I mentioned. So returning to this question, are crowd workers capable of finding accessibility problems in online imagery? And with 1 labeler per image, our results were 85% down to around 73% for object and path. And if you look at the overall average, it was about 78%. If you discard label type and you don't care about the category, but just whether or not someone was able to find an accessibility problem, you get a marginal increase, as expected, 81%. So some common problems included, well, the task was to find problems, and it turns out then people are really motivated to find every problem, even though they're not problems. So like this stop sign here is not actually in the sidewalk path. Similarly, those trees that are labeled are not actually in the path. Less commonly, though, we had random labels and category errors. So we also examined some simple quality control mechanisms, like hiring multiple workers per image and then looking at majority vote across 3 labelers, 5, 7, and 9. So again, that overall average with 1 labeler was 78%. And as expected, you do get that rise, sort of saturates around 5 labelers. And then again, we also looked at the binary version of this. OK, so we also evaluated this verification. What effect does that verification interface have? So and on the x-axis, I have time cost. So it gets more expensive as you move to your right. So with 1 labeler and 3 verifiers, we get a significant improvement over 1 labeler. And 3 labelers and 3 verifiers outperforms 5 labelers. But of course, this is expensive. But we've demonstrated that with basic quality control measures, minimally trained crowd workers can find accessibility problems with around 93% accuracy. And then the key question that we had was, how can we do better? And how can we scale our approach? And this introduces this last question. And some initial work towards this goal is a system called Tome. Tome is comprised of 6 steps. In the first step, it's a web scraper that downloads Google Street View images and some associated data with that, including a 3D point cloud. The GSV has a LiDAR scanner on it, so we get the 3D point cloud, some top-down Google Maps imagery, and some GIS metadata that includes like location data as well as topological information about the intersection. For our evaluation data set, we scraped 11.3 square kilometers across 4 cities. We collected 1,086 intersections, nearly 2,900 curb ramps, nearly 650 missing curb ramps, and our average age of the Google Street View images was 2.2 years old. So the third step is an automatic classifier for curb ramps. But as you might imagine, this is a difficult problem. So while you're going to get some true positives, you're also going to get false positives. That is, the algorithm is going to mark an object as a curb ramp that's not a curb ramp. And most importantly for our work, we get false negatives. That is, the algorithm altogether misses marking a curb ramp. So to deal with this problem, we trained a task controller, which essentially tries to smartly route work to either a verification step or a manual labeling step. So if it predicts that the computer vision algorithm did well, it'll route it to verification. If it predicts that the CV algorithm did poorly, it discards those labels and sends it to a manual labeling step. So let's take this as an example. Here we have those 2 false positives and 1 true positive and a false negative. Let's say it predicted CV success. It ends up in crowd verification, where the crowd properly gets rid of those 2 false positives, resulting in this final output. If the task controller predicts poor CV performance, it's sent to the crowd labeling step. And here the crowd correctly labels those 2 curb ramps, resulting in this final output. One crucial thing to note is that if we end up in this top workflow, there's no way to correct false negatives. And that has implications for how we bias our computer vision algorithm, as well as how we bias the task controlling system. So let's dive into this a little bit more deeply. First with the automatic curb ramp detector. So this has 3 stages: a deformable bar model, a post-processing DPM, and an SVM-based classifier. And the DPM models a target object and its parts with hog features, histogram of gradient features. And it also models spatial relationships between those parts. It has displacement costs. So in this case, a trained DPM has 2 components, and it's able to compensate for both viewpoint variation, so a side view of the bike, as well as a frontal view, as well as compensate for pose variation. This is one of the reasons DPMs have been so popular for doing a person tracking. So we can recognize the bike even though it's in the wheelie position. So we use this DPM, and we had a 3-component model, and we think it implicitly captures the different viewpoint variations of curb ramps. So the DPM sweeps through an image, and here we have bounding boxes that are marked in red, where brighter red is higher confidence. And in the bottom left, I'm going to be tracking the algorithm's performance. So we have 1 true positive, 12 false positives, and 0 false negatives. But as you might imagine, or as you might be able to see, we have multiple redundant bounding boxes. But more alarmingly, we found curb ramps in the sky. And what are they doing up there? Why are we investing money putting curb ramps in the sky? But so we use the LiDAR data then to filter out anything that's above the ground plane. And we also use non-maximum suppression to get rid of some of the overlapping bounding boxes. And this drops down our false positive rate to 5. And then we also have this last step. It turns out that intersections are highly constrained geometric configurations. So this SVM tries to account for some of that context and eliminate things that even look like curb ramps like this driveway. So now we're down to 3 false positives. Yeah?
It seems to me that compared to arbitrary computer vision, you know more in Google Street View about the scale. But it doesn't sound like you're using that information.
Yeah, what do you mean about that?
I don't expect a curb ramp to take up the entire image, whereas a bicycle might.
Yeah, so you're talking about the DPM and how we train the DPM. So the DPM, for example, is very naive. It only uses pixel information, the gradients of the pixels, and it's a sliding window approach. And that's why we try to compensate for that and added those 2 additional stages. You might also ask, well, why don't you use the LiDAR data in your process to identify the curb ramps themselves? Well, it turns out that LiDAR data is too coarse, so we couldn't do that. We tried. Maybe later versions of it will be higher fidelity. And here's another example where we have 6 true positives, 11 false positives, and 1 false negative. And here's the final output with 6 true positives, 4 false negatives, and 1 false negative. And the false positives are easy for humans to correct, but the false negative takes more time. So this brings us to this task controller system. And this is also an SVM-based system. And it has a 23-dimensional input feature that includes things like the descriptive stats of the bounding boxes from the DPM, as well as 3D point cloud data and the intersection complexity. And both of these things are proxies, basically, for intersection complexity. So if it turns out there's a lot of variance in the depth of a street scene, it's higher error with our computer vision algorithm. OK, and then so if the task controller predicts good computer vision performance, we go to this crowd verifier. And here the crowd can pan and just simply click on incorrect detections. And then the labeler looks like this. Similar to before, you can pan and then just outline curb ramps and missing curb ramps. So the study method was also similar to before. We used 2-fold cross-validation for training the computer vision algorithm and the task controller. We deployed Tome to Mechanical Turk, and we compared Tome to 2 baseline conditions. So the first baseline condition is manual labeling only, so all work is routed to the bottom workflow. The second is computer vision plus verification, so all work is routed to computer vision plus verification. And then finally, we have the Tome system with that smart task allocator. So for manual labeling, I have precision in blue, recall in orange, and F measure in green. We have 86% F measure. As expected, the CV plus verification drops. And then for Tome, we get similar performance to manual labeling alone, but a 14% decrease in cost. In terms of the task controller performance, 80% of the scenes that were routed to the verifier were correct, and only 50% of the scenes routed to the manual labeling step were correct. So to investigate the effect of the task controller, we simulated a perfect system with 100% success, and we found a speed up from 14 to 27%, which essentially means that a lot of the speed up gains are going to come from improvements in computer vision, which has been a huge focus for us. And we recently got a paper at CVPR this year on using convolutional neural networks to model some of the more context that maybe Dan was alluding to in an intersection to try to find missing curb ramps. All of this work has now culminated in a tool called Project Sidewalk, and I really encourage you to go check it out. It's at projectsidewalk.io, and it allows anyone from empowered, interested citizens to government workers to virtually walk city streets and find accessibility issues. And we're using, now I'm going to mark a surface problem, for example. I'll then mark a missing curb ramp. And we're using game design principles like short and long-term goals, seamless onboarding, and performance tracking to try to sustain participation and increase the overall user experience. So far, in a limited beta rollout in DC, yes, Jeff?
Yeah, so early on you talked about the different categories of obstacle, for example, that you could annotate. And then when you talked about Tome, it was really focused on the ramps. So I just
Right.
wondered, A, is ramps the most important problem? That's why you focus there? Or is it just the most amenable to computer vision? Or
Right.
which balance of those?
Yeah, so it was the most we thought it was the most constrained problem. If you check out the tool, you'll see that there, for objects in path, there's just such a wide variety of problems. Same with surface problems. So we thought that starting with curved ramp, it was more of a technology-driven than it was actually need-driven. Okay. So yeah, and so I guess a big part of this is now we're getting so much more data, as I'll get to in 2 more slides, that I think we'll have a better chance of doing different kinds of experiments. So far, in this limited beta rollout, we've had 470 miles. That's more than going to DC to Boston. And they've contributed over 66,000 labels. And this is giving us really interesting platform to experiment with new data analytics techniques, as well as new hybrid workflows and new kinds of verification interfaces. So we're like popping up different kinds of user interfaces. In this case, you can accept and reject category issues in a rapid way rather than having to like pan in a window. And then Google, I don't know if you guys know this, but Google recently allows you to actually go back in time through their entire data set. And we think this is a really cool opportunity to allow urban planners to study how accessibility changes in cities over time. However, this has even greater data demand. But I do have one student who's been working on labeling one of these time series shots and then either back or forward propagating that label through time. So I think that's going to be some really interesting work in the future. And then finally, and I guess what's driving all of this is the novel assistive technology tools. So one of these things is, this is unprecedented data. So how can we come up with new models that capture accessibility? So like access scores of cities, new kinds of interactive visualizations, new kinds of smart routing tools, doing things like city comparison. Is Seattle, for example, more accessible than a city like DC? And all of this data is open. So I encourage you to go check it out and maybe even build your own tools with it. Okay, so that was Project Sidewalk. I want to turn now to Handsight. So Handsight is focused on, skipped ahead there. Handsight is focused on sensing and feedback information about the physical world that is non-tactile. So for people with visual impairments, touch is a primary means of acquiring information about the world. In fact, prior work in neuroscience and psychoperception has found that blindness actually enhances tactile acuity. However, fingers can only feel tactile phenomena like bumps and temperature and shape. And there is much richness in the world that is non-tactile. So in our work, we were exploring how to computationally augment a blind person's sense of touch to interpret non-tactile information about the world, such as color and text and texture. Imagine, for example, gliding your finger along printed text and hearing the words read back to you in real time, or feeling the shape of a bar graph in a printed book or newspaper, or touching a piece of clothing and hearing a description of the underlying fabric. So in the Handsight system, we're using a finger-mounted wearable camera to try to assist blind users in learning about non-tactile information. And the camera itself is an endoscopic camera used in non-invasive surgeries. And this tiny form factor allows us to explore new kinds of designs, including cameras mounted under acrylic fingernails, instrumenting more than one finger, and also ring-based designs. The cameras themselves are accompanied by haptics to guide the user's touch explorations, either on the finger or on the wrist, as well as a smartwatch for processing power and additional feedback. So we've had a number of focus areas, and this is all application-driven research focused on supporting activities of daily living. So we've looked at things like reading support, color and texture recognition, touch-based control, and haptic and auditory feedback. I'll just touch on a few of these briefly. In initial work, we did reading support. So I'll show a video of that.
Amy, gone over the wood, testified that dogs are just as prone to jealousy as humans.
So while our initial users were really excited about the potential of this system and in terms of the control that they had of reading, they also had trouble staying on the line of text. And so our follow-up work really focused on ways of guiding a user's finger, first in one dimension. So we have pitch control audio as well as haptics mounted on the finger. And what we found was that although pitch-controlled audio resulted in more precise movements, our participants actually liked the haptic guidance better, perhaps because it's a different information modality, and it didn't interfere with the speech synthesis from the reading support. So in follow-up work, we've looked at instrumenting the wrist. So the idea here would be that the haptics itself would be under like a smart band on the smartwatch. And we've compared both 8 motor designs as well as 4 motor designs. So our experimental test bed looks like this. So you get haptic stimuli on your wrist, and then you have to follow those directions in 32 different movement directions. And again, we compared 8 motor to 4 motor. So as you might expect, 8 motor, which has double the number of motors on your wrist, actually performs better, which this is statistically significant result, but not as much as you might expect. And so now we're looking at adapting some of these feedback algorithms and also looking at 2 different kinds of tasks, target finding and path tracing. And then the final little piece that I want to talk about is if you have the hand sight system and you're wearing this, we need a way to control things. And so we're looking at different methods of control as well as to increase mobile information access in general. And we're specifically focused on on-body interaction.
Health and activities, voice input, notifications. Notifications menu opened. You have 1 missed phone call and 2 new messages.
So this leverages the blind person's sense of proprioception and increased tactile acuity. And we've also tried to come up with intuitive mappings between the interactions themselves and the information access. So for example, time information is accessed on the wrist.
Clock. Clock menu opened. Timer. Stopwatch. Alarm, set for 8 a.m.
And so again, acknowledging the large team of students and collaborators with Professors Rama Chalapa, Leah Finlater, and David Ross, who's at the Atlanta VA. Okay, so the last project that I'll talk about is somewhat similar in spirit actually to handsight, but it's focused on deaf and hard of hearing users. And we've been exploring methods to increase sound awareness for these users using a head-mounted display. So in an initial prototype, we built a display that looks like this that conveys sound direction and magnitude.
Right back in case you need me.
I just realized something. We've never had a completely successful test with any of the equipment.
I blame myself.
So do I.
So the key thing here is that this was a wearable prototype using an HMD display, but the microphone array and the sound processing itself was non-wearable. So that Death Star in the middle was the microphone array with 64 microphones. But this allowed us to test the initial feasibility of our ideas and to actually run user studies with a working prototype, as captured by this participant.
When we went back and forth, it was clear, it was like boom, pum, pum. And then to the Ghostbuster run, when you were standing behind me and you spoke, it was just like right there. So I knew you were speaking.
We had scripted conversation using things from Ghostbusters, so that's why she mentions Ghostbusters. So this again is a large piece of work here done with my collaborators at both University of Maryland as well as Gallaudet University, which is the largest campus for deaf and hard of hearing. And now we're looking towards building a truly wearable design with an embedded microphone array on the wearable itself, either 8 or 16 microphones, and trying to look at new kinds of precise localization algorithms as well as more kinds of feedback visualizations. Okay, so that was the accessibility thread of work, and now I want to transition into talking about STEM education. So I want to motivate this by sort of pointing out some of the research in involving children in STEM experiences as early as elementary age. In fact, the National Research Council recommends engaging children from kindergarten onwards into scientific and engineering practices. However, science educators and researchers continue to face real challenges with this. Children seem to see science as disconnected from their life, as boring and irrelevant. And in fact, science is also oftentimes presented in a very formulaic way that reduces child agency in the scientific experience process, in this inquiry process. So what we're interested in doing is exploring the role of wearables in increasing the relevancy of scientific inquiry. And we think there's a lot of potential for wearables in this because it collects unprecedented data about the self that is inherently personalized and life relevant. It goes where the child goes, and it also engages the body in learning, this idea of embodied learning, that human action is tied to human cognition. And so we've worked on 2 projects that I'll talk about today, BodyViz and MakerWare, and Maker is the focus of my NSF career research. So I'll be focusing on that more than on BodyViz. Before I move on, I just want to acknowledge that this is a super complex problem that requires a multifaceted solution, including policy, teacher training, new classroom practices, and also rethinking ways in which children can be involved in the scientific process. And for that reason, we've engaged with teachers throughout our research and design process, STEM educators, who help us not only design our technology, but also the learning activities that we have with them. So for BodyViz, the idea is how can we design wearables that use the human body and physical activity as a platform for experimentation and scientific inquiry. For example, we want to build wearables that allow kids to ask and answer questions like this. Does my heart beat faster when running versus reading a book, and why? How does my breathing rate compare to my classmates, and why might this be? And how does food travel through my body? And this is work done with my College of Education and iSchool professorial colleague, Tamara Clegg, as well as our students. So we built 4 prototypes over the last 3 years, including prototype 1, which has a very plush kind of tactile feel to it and uses a finger IR sensor to visualize heart rate and oxygen delivery to the lungs. And our more recent prototypes are far more streamlined that better encourage physical activity and the kinds of experiments that we want children to do. And it senses both real-time breathing as well as your heart. And it looks like this. And we've looked at automatic methods for sensing eating, but currently that's invoked by pressing a snack time button, where children get a view of the digestive process. A smartphone is used to show a video of food being processed. And then we also use vibromotors and sound to enhance engagement. I'll leave that up to your imagination. The organs themselves are removable, so it allows children to explore the multi-layers of the body. And crucially, if they're returned to the proper place, they instantly start working. Okay, so as I mentioned, I have this smartphone here, and that actually plays a pretty crucial role. That's communicating in real time with this wearable physiological sensor, which is a Zephyr BioHarness 3, and is a military-grade physiological sensor that communicates wirelessly with the phone, which does some processing, which then communicates wirelessly with an embedded Arduino on the shirt. And we've done a lot of different evaluations over the course of this project in lots of different kinds of learning environments, including after-school programs, science camps, and elementary schools. And I don't have time to go into all of these results, but I just want to touch on 4 areas. And the first thing you'll notice if you come on a deployment with us is just how BodyViz engages children in learning about the body. But also, children effectively use this shirt as a platform for experimentation. So they'll brainstorm, as we scaffold them in these learning activities, different experiments they can run on the body, and then they analyze that through the shirt through the visualizations that are manifest on the shirt, including things like running or eating and jumping jacks. Like, what effect do those have on my breathing rate, for example? We also look at content learning. So while the primary goal of BodyViz is to engage children in the scientific inquiry process, we've also looked at content learning in terms of body knowledge. And for this, a popular approach is called body map drawing, where a child actually sketches their understanding of their body knowledge on a sheet, and then we do pre- and post-test comparisons. And we've had pretty positive results so far. 73% include at least one new organ, 56% correct positions of organs, and 30% improve organ shapes. So I want to touch on 2 unexpected findings. The first is this disembodied use, where a child will put on the physiological sensor but not the shirt. And this is in part because of the asymmetry here. Like, if I'm wearing the shirt, you actually get more benefit than I do. So you'll actually see people, do these kinds of things like actions, and then they get to see the shirt on a mannequin. And this led us to develop a new system that's a mixed reality learning environment where we have multiple wearers of the physiological data, which is transmitted in real time to a large screen display. And then they can do collective in situ hypothesis testing and analysis. And we have 2 papers on this, including at CHI 2017 this year. And the second thing, which ended up being the key driver of my NSF career research, was this just profound curiosity about how these shirts worked and how we built them. And that happened across all of our deployments. So this really led to MakerWare, which I said is my NSF career work. And the key idea here is, how can we enable young children to build things like BodyViz, essentially, right? And this is with, again, my College of Education colleague, Tamara Clegg, and our students. So to motivate this a bit, wearable construction kits like LilyPad Arduino or Adafruit Flora have been incredibly popular, and they've shown promise in changing perceptions of computer science and bringing in underrepresented groups to computer science and allowing users to create self-expressive and personally meaningful designs. However, these toolkits require embedded programming, basic circuit and electronics knowledge, and manual high-fidelity skills like craft work and soldering. So this allows for really high ceilings and extremely expressive and really interesting designs, but it also creates barriers for young children and even adult hobbyists. In fact, I use LilyPad Arduino in my teaching, and even graduate schools struggle with the sewing components and other things. So this affects rapid prototyping and tinkering, but it's also a high barrier for children. In fact, if you look at the literature in studying e-textiles as a learning platform for computational design, you'll find that a majority of work is with high school students or older. So we had 3 overarching questions here that I'll talk about. How can we enable young children at the elementary age to design and build their own interactive wearables? For example, what are the appropriate abstractions? How do they actually program them? What do children want to build, and how can we support these goals? And finally, how does working with our tools and techniques impact skill development and perceptions of STEM? So to address these questions, we've pursued a 2-year iterative design process where we began with participatory design sessions, where we've run 5 of them in total, as well as 2 participatory design sessions with STEM educators, which led us to the development process and some refinement and pilot studies, and then some field deployments and workshops. So in participatory design, we use a method called cooperative inquiry, where intergenerational groups of adults and children work together to design and test technology for children. And in our initial sessions, we used a lot of blue sky methods, lo-fi prototyping, using like foam and cardboard to identify what do children want to build. You know, if you take away the technical constraints, what are they focusing on with wearables? And then later, as we develop prototypes, we'd have them to test out these initial prototypes and give us feedback. STEM educators helped us co-design the learning activities and some of the curriculum, and they also gave us feedback on the prototypes themselves. And we developed 5 themes that came from this, including reacting to body movement and physiology, recognizing gestures and physical actions, supporting social interaction, augmenting the play experience, and responding to the environment. So any wearable toolkit for children should really try to design towards these things. So this led us to the MakerWare system, which is informed both by these participatory design scenarios as well as literature and developmental psychology and programming toolkit work. In its tangible programming approach, it's comprised of 2 things. First, these tangible plug-and-play modules that are magnetic and work instantly as you place them to allow for really emergent and complex behaviors. And the second part is this socket mesh, which is pre-sewn into fabric and allows children to easily attach and detach these tangible modules. This also provides power and the wiring for the system. So the tangible modules themselves are hexagons, and each one has 1 input and 3 outputs. When a module receives its input, it processes it and then forwards its output to all 3 outputs, which allows for really interesting nonlinear forms and cascading designs. And we have 5 module types: power, sensors, which sense and translate physical phenomena into electronic signals, modifiers that translate those signals into other types of signals, actions which translate signals into perceptual forms, and a miscellaneous category. And we've developed 33 modules in total so far, including things like motion detectors, sunlight detectors, sound sensors, light sensors. Different actions include motors and lights and vibromotors. 7 different kinds of modifiers. A few ones to know about are the volume knob, which is a potentiometer, but we call it a volume knob. A threshold and inverter. So a threshold allows children to design with conditional logic, and the inverter inverts the signal. 4 miscellaneous, and the 1 power. So how do you create? Oh, before I get there, I just want to focus. Another way to emphasize the different modules is around these themes that came out of our participatory design. Okay, so like movement and physiology, social interaction, and so on. Okay, so each module is custom designed, and the top layer is an exposed electronic component that captures the module's behavior. And the second layer is a custom laser cut with a child-friendly name and icon. And the third and fourth layer are custom PCBs. The third layer has a microcontroller and requisite surface mount components. And then the fourth layer has a neodymium magnet and contact springs. So when you place this module into a socket, it works instantly. And the sockets themselves, as I mentioned before, provide the wiring, the ground, and VCC. Okay, we've developed two kinds of sockets, some that are pre-sewn into fabric, and then in our workshops we also have this fabric patch that can be attached post hoc with Velcro or safety pins. So let's create something with MakerWare. So everything has to start with a power, and then the next thing could be a sensor or an action module, and this is our first complete program. It just turns on a light, and in this case the light is always on. If we want to make this interactive, we have to add in a sensor, and here we've actually built like light up shoes, motion reactive close. If we want that kind of cool fader effect, we add in a modifier, in this case a fade modifier, and this will give us that cool fade effect. And of course we can add a lot more action modules, for example a spinner or a vibromotor or lights. And because we do this 3-output system, you can create really cool and interesting flexible designs for your clothes that are functionally equivalent. So this design is functionally equivalent to this design and so on. And we can create a diverse set of designs tangibly. So for example, this is an auto headlight lamp that's using a light sensor and an inverter. This is chameleon clothes that changes color based on the color of proximal objects. This is a laser tag armband here, focusing on that social interaction part where you're actually building something for laser tag. And so this is using an IR beam that shoots when you hit the button, and then we have an IR receiver that glows red when you're hit. And as you gain more experience with the toolkit, you can create even more complex things. So for example, we can actually keep track of how many times we've been hit. We can set up conditional logic that says, okay, I want the game to be over after I've gotten hit 7 times, and it'll sound an alarm when that happens. Okay? So high ceilings, hopefully. All right. So, and I'll just show you a quick demo video of how this works. And just focus on how things instantly work as soon as I place a module. That's using a distance sensor. Then I'll add in a spinner and a sound maker. You've got like a propeller armband. Like fly away. A sound sensor, and so on. So that just gives you an idea of how this works. So in terms of our evaluation, we did these workshop-based evaluations with 32 children. The average age was 8, and we had 16 female. We did 2 single-session workshops and 3 4-session workshops. The workshops themselves were divided based on age. And we also did a pre-questionnaire that measured technology experience. 90% reported using a computer at least once a week, and 50% reported previous experience with programming toolkits like Scratch or electronic kits like snap circuits. In terms of the sessions themselves, they're about an hour and a half. We have a pre-study questionnaire, an intro to Makerware, and then 70 minutes of playtime, where we also had interspersed design challenges, which were used to assess understanding of Makerware, followed by a 10-minute post-study questionnaire. We also had, in the multi-sessions, anything you see in green is dedicated to these final projects. So they first started with sketching ideas for what they wanted to build for themselves. Then they actually built those things and presented them to an exhibit to their family and friends, which were invited. For data and analysis, we used a mixed method approach, and we looked at session video, design challenge performance, end user creation, artifact-based interviews, and pre- and post-study questionnaires. Okay, in terms of our findings, we found that children across all ages were able to create a wide range of creative designs. They were highly engaged in the making process, and they applied computational thinking skills. I'm going to focus on these 3 findings here. Towards the first, we used at the beginning of the multi-session workshops these little fix-it challenges where we would give you an actual tangible design that had some problem and you had to fix it. So in this case, we have a sensor and an output from an action module that are pointing at one another. So the solution to this is to flip around the action module. Similarly here, we're trying to get the light bar to respond to the distance sensor, and we have an ordering problem. We have to switch the distance sensor before the light bar. And then we also looked at their understanding of cascades. So we asked them to make it so that the lights would react to this volume control. And so this is one example solution. So we found that 81% of our youngest users were able to accurately answer these things, and 100% of our middle and oldest users. We also looked at branching understanding. So for example, we'd ask questions like, do these 2 designs behave differently? And we found youngest were able to with 43% success, middle and oldest were 100%. In terms of progressions, we found that understanding changed over time, as you would hope for. So for example, on the first day, 47% answered sequencing questions correctly, but by the last day, it was 77%. And for conditional logic, which was only asked of the 2 older groups, 20% on the first day and 78%. This is exactly what you'd want, right? Hopefully. is some demonstration of computational thinking development over time. So I think the coolest part about building a toolkit is enabling creativity. And so I'm happy to present some of the projects that they've worked on. First, we did a quantitative analysis of what they built. And as you might expect, as a child was older, they used more modules as well as more complex modules. So they built more complex designs, like using inverters and thresholds for everything except for use of lo-fi materials, which was the lowest amongst the oldest group. Okay, what do children make? So in terms of the designs themselves, most popularly was sports and fitness, followed by role play, socio-dramatic play, and then other. In terms of the sensors, like what sensors did they want to sense about the world? Movement, manual input, environment, and physiology, and then social. And so you're actually seeing children take advantage of some of those affordance of wearability, like movement sensing and physiological sensing. So I want to highlight a few projects that demonstrate the breadth of designs and technical sophistication amongst these children. So first with role play, here we have Daniel, who's 7, and he made a super ninja uppercut band that when you did ninja moves, it would light up. And he also had a ninja belt that you might see here that had a propeller with a cardboard on it that would spin and react to his movement. So he was 7 years old. This is Austin, who is age 9, and he made a magic Pokemon doll.
Whenever I'm putting this dagger at the receiver and I think I'm going to activate something on this one, it sends it to this one and activates something else.
So his vest is remotely controlling his Pokemon doll, and it's using that IR functionality. And then he's also using a square wave generator to get the lights to flash on and off and the sound to flash on and off. In terms of sports and fitness, which is our most popular design, we have Sarah, who made a smart lacrosse stick.
So if I'm cradling the stick and she comes up to try to check me, the distance sensor will notice if she's there, which means I can run away.
So this is pretty cool, and she brought in her own artifact to custom design, and she's using a distance sensor and some lights in the sound maker. And perhaps our most complicated design was this next generation jogging clothes that Amelia, who is age 10, made.
I made a bunch of clothes that you could wear if you're jogging at night. So my hat has a sensor that when it's dark and you're moving, a bunch of lights turn on and vibration, and then a bunch of lights and vibration turns on my vest.
Let's start on.
Oh! So this, it's like a little fan. And you could change how fast it's going, so that way you could just put it next to your face if you start sweating. That's how fast my heartbeat is, with music and a light.
And then what are the numbers on there?
That's counting the beats.
Your heartbeats?
Yeah, so it could go all the way to 99.
Okay, so there's just two things I want to point out about this. I mean, one, it's very creative, and it's using 40 modules and 4 meshes and so on. But you may have missed it, but the motion reactive close actually use an AND condition. So she's cascading multiple sensors together to create an implicit AND. So she needed to both be running and for it to be dark for these safety close to turn on, which I thought was pretty cool. And then this heart tracker armband beeps and lights up on each heartbeat, but also counts the heartbeats up to 99, which is neat. So finally, some unexpected things. First, this 8-year-old made a custom oscillator.
And the fan spins the little piece of tape and paper over the distance sensor, and then every time it flies, the sensor senses it, turns on a light.
Before we ran into this 8-year-old, this is in a museum exhibit, we hadn't yet made wave generators, and after we saw this, we built in a modifier that was a wave generator that you could get that behavior. So that's pretty phenomenal. And then also in the museum exhibits, it was open to anyone. So we had people of all ages use our system, including this 4-year-old. And I just want to bring this up because the mother said he hasn't been captivated like that for any other activity in the museum. And he worked on his scarf for about 30 minutes before we basically shut down the exhibit. And I'm only pointing this out because all of our workshops were with 5+, but there might be opportunities to get even toddlers or 4-year-olds more involved with makerware. In terms of future work, I'll just go through these very briefly. We have 3. We're very interested in reducing the size, the weight, and increasing flexibility of our designs. A big piece of my NSF career is something that we're called hybrid programming, where you're using the tangible modules in concert with the graphical programming interface from a touchscreen to allow children with more experience to actually program the microcontrollers. And then something else that's a key part of my NSF career is how can we allow children to automatically recognize different activities? And we're using this touchscreen interface to give the children feedback about the recognition algorithm so they can use programming by demonstration in interactive machine learning. And in this example here, I'm illustrating, you see the child programming his wearable to recognize jumps. Okay, so I've talked about 4 projects in my research group, which are fairly diverse, but they're united with a common approach of sensing, processing, and visualization, as well as a common goal around addressing pressing societal challenges. And I want to thank my partners in this work, particularly in STEM education, that really enable what we do, including the DC Child Museum, a local school district, and the Boys and Girls Club, as well as my funding sources, Google, IBM, NSF, and the DoD. So thank you very much.
Great. So we have some time for questions.
Hi, Magda. Or Jeff.
So one question is kind of regarding educating young kids. What's your take on getting them to play with modules that are pre-built and all they have to do is kind of snap things together versus trying to get them to really understand how things work at a very fundamental level? So I think your 2 projects kind of hit the 2 ends of the spectrum versus, understanding how the body works versus snapping pieces of sensors together to create higher level behaviors.
I think that's a really, really great question. It's a tension that I bring up a lot in my NSF career proposal, actually. And it's like, I think it's a question about transparency, about trying to develop something that is appropriate for the developmental stage of the child. And one thing, I'm just going to slide back to this slide because I skipped over this so very quickly. But you might not notice, because I didn't really mention it, that there's a DIY electronic module. It's basically a small breadboard. So children could actually design their own modules if they wanted to with electronics. And in some of the pilot studies, we actually brought electronic components, but there just isn't time. Like even in our multi-session format where we had 4 workshop days, we just have so much content to sort of cover that there's not time to get into circuit design and, and notions of how the underlying circuit theory works. But I think if we're in, say, like an 8-week format or something, we would definitely want to use this, and that's why we designed it in the first place. And I'm really interested in sort of scaffolding that experience, and I think the touchscreen, too, can provide greater transparency in helping debug problems in a design. So great question.
So people build up their courage. I have a question for you, which
okay.
is... There
is one over there.
Okay, well,
yeah, go ahead.
Well, there's this really beautiful diversity of projects, and I was just wondering if you could give us some insights into your process of how do you choose which of these projects to really tackle?
I think the kids' interest was both personal and professional. So as you know, I'm a parent, and so like my whole life revolves around my kids, and so it's made me think a lot about how to design for them. And as well as professional, it was really out of BodyViz and just sort of seeing how children were using BodyViz and their interest in the e-textiles and whether or not that could be a platform for engagement. But yeah, I mean, it's a question of like where do we get our inspiration? I think choosing problems is like a key thing for a faculty member, and I tend to just kind of follow my intuition. Yes.
So, do you have any plans of contacting people in the Department of the Interior? So this has to do with the accessibility study you were talking about and using Google Maps.
Yeah.
Is it possible to send all that data as a giant list of things that need to be repaired in a city? Yeah. Is that something that you explore?
So it's a great question. So I mentioned participatory design for my other projects, a few other projects. We actually also did that for Project Sidewalk. I just didn't have time to cover it. So we've met with DOTs, the DC DOT, and they're very interested in the work that we're doing. We've gotten positive feedback from multiple cities that want Project Sidewalk deployed in their city. So it turns out that there's an ADA compliance issue, so cities need to be accessible. There's just no way to know that, right? And so I think this tool is really going to provide more accountability for cities and a better understanding of where people can and cannot go. Great question.
Yes. So talking about the accessibility work, you earlier alluded to the fact that Google Maps is usually updated for big cities. What about more rural areas that maybe don't get as much coverage with Google Maps?
So I know I had a lot of slides, but there was one where I was like, the average age of our data set was 2.2 years old. The reason was we included Saskatchewan, which is Saskatoon, which is my wife's city, and because we wanted to include cities we could easily physically audit and so on. And the average age there was 4 years. So that actually pulled up our whole average. DC is getting refreshed about once every year. Google does not publish this information, but it appears to be about once every year for the major cities. There's actually other companies that are driving through our cities all the time and collecting similar kinds of street view data, but they're just not public. But our tool would work if we had access to that data, right? There's nothing inherently different about street view. Hi, Alan.
Can you talk a little bit about the sustainability of the projects? And what I'm talking about here is, suppose you make something that disabled people are relying on, and then what happens when you publish your paper and need to move on?
Yeah. I guess that kind of is a callback to some conversations we had at lunch. I think that's a difficult challenge. I think Project Sidewalk is kind of moving towards this almost nonprofit. Like, it's a public tool now. It requires a ton of development and maintenance. We get feedback from lots of users. For those faculty who've actually deployed tools, and students, you're probably familiar with this. And I think it's a great question. I mean, I'm constantly looking for new funding sources beyond just NSF, which is the current funding source for this. Google's also given us some money, but I haven't really figured that out yet. It's possible that we could try to come up with a business model of actually working with cities where they might be able to pay developer staff so that the model becomes more sustainable. But that's a really good question. And we've had those discussions, the team.
With that, let's thank our speaker.